Swayam Prabha. Digital India. Educated India.
So, good afternoon. Today I will be discussing with you the combustion chambers in CI engines. So far we have discussed the typical designs of spark ignition engines and what are the typical features and how we can design good combustion chambers for SI engines. Now we will discuss the good combustion chamber designs for CI engines. So, basically in the SI engine the fuel air mixing is done by carburetor or by fuel injection system, but in a diesel engine it is altogether different case. Here the mixing of the fuel in the air is the responsibility of the combustion chamber design itself, and you know that in a diesel engine the most important process is fuel air mixing, okay? And therefore, the design of the combustion chamber in a diesel engine or CI engine is extremely important, okay? So, combustion chamber design in a CI engine aims to provide adequate mixing of fuel and air in a very short time. You have to understand that if the time is long, obviously your delay period will be more, and if the delay period is more, the engine will be knocking, because combustion in CI engine knocking happens in the beginning of the combustion. So, if the mixing is not good, obviously the delay period will be more and therefore the knocking will be there. So, you can see that a good engine design for a CI engine will not knock, and a bad design will definitely lead to knocking and all other kinds of other issues. Now, this mixing has to happen in a very short time. It should not take more than 4 to 6 crank angle degrees, and you know that it is a extremely short time in terms of fraction of milliseconds of a medium speed engine. So, to achieve such an efficient mixing, air swill is provided. So, what you need to do, how does a good engine combustion chamber design ensures that the mixing of fuel and air is proper? So, it induces swill. Swill is air movement. So, obviously a good engine design should give, good combustion chamber design should be able to induce adequate level of swill in the combustion chamber, so that your droplets interact very quickly with the hot air, hot high pressure air which is present in the combustion chamber at the end of the compression stroke, so that it can evaporate quickly, heat transfer and mass transfer can take place quickly, and it can form combustible charge of fuel and air, okay. So, air swill is generated by air swill basically generates high relative velocity between the fuel droplets in the air, and that helps us mixing. Fuel is injected in the combustion chamber by an injector. So, in a CI engine you have an injector which is injecting the fuel, and this injector could be, there are several designs, this could have one nozzle, it could have multiple nozzles, that means only one jet will come out of it, or it could be that there are several jets which are angled at different areas, which are targeting different areas, okay. So, when the liquid fuel is injected in the combustion chamber, spray cone gets affected due to air motion. Obviously, if I am having a spray cone and there is a swivel around it, it will get affected by it. I will show you some pictures of that as well. So, basically the air motion or turbulence or swivel is going to affect the spray, okay. Now, here at this point in time I would like to ask you, what is the difference between swivel and turbulence? So, the difference between swivel and turbulence is that swivel is directional air motion, there is a particular pattern or direction of air motion, and turbulence is chaotic, it does not have any direction, okay. So, this is the difference, and you see in the engine combustion chamber you have to also understand that too much of swivel is also not desirable. Why it is not desirable? Because it will disturb the air layer which is present around the cylinder walls, and it will lead to increase in heat transfer from the cylinder wall, and therefore, the engine heat transfer will increase, okay. So, one has to understand that you have to have adequate level of swell. Okay. If you remember the discussion that we had about spark ignition engine, in spark ignition engine we also wanted swell, but very close to the spark plug we did not want swell. Why? Because when the spark is generated, a nascent flame, a small flame is generated, and if there is too much of swell in that zone, this is going to extinguish the flame front and you will have a misfiring event. But there is no such limitation here. Here you can have good swell all over the chamber, and so swell is extremely important here. Then onset of combustion, when combustion starts, in a spark ignition engine there is only one flame front that moves. There is only one 2D sort of combustion flame front which is moving, although it is curved, but you say it is 2D because this is really a thin zone. Okay. But here in a CI engine it is a heterogeneous combustion. That means the droplets that you are injecting in the combustion chamber, each droplet is burning in the space independent of the others, more or less. Okay. So that means each droplet will burn in some part of the combustion chamber, it will generate heat, it will generate high temperature, okay, it will generate high pressure, and this will lead to additional swirl or turbulence generation inside the combustion chamber. Okay. So, swirl and turbulence can be generated by the air motion because of the design of the combustion chamber, but even the combustion can lead to a generation of additional turbulence which is guided by the shape of the combustion chamber. Whether that will be turbulence or swirl, again it is guided by combustion chamber shape. So, therefore, shape of the combustion chamber is extremely important for the success of a compression ignition engine. What are the important factors if you want to design a good combustion chamber for a diesel engine? What are the factors? What are your objectives? What are the factors that you should keep in mind? So, first factor obviously is heat loss to the combustion chamber walls. Now, heat loss to the combustion chamber walls means what? What can you change? Heat loss is directly proportional to the surface area. Okay. So, what does it mean? I mean, nobody would like to have more heat loss from the cylinder walls, and therefore, you would like ideally to have as small surface area exposed to hot gases as possible. So, this is one. Then injection pressure. How much, at what pressure should I inject the fuel? Should I inject the fuel at low pressure of say 200 bar, or should I inject the fuel at 2400 bar or 2000 bar? Okay. That question is also answered by what is the design of your combustion chamber. I will tell you an example. There are two types of combustion chambers. One is called direct injection engine combustion chamber, the other one is called indirect injection combustion chamber. I will discuss about them in a couple of slides from now. But direct injection does not have very high degree of swell. It has some swell, and therefore, the mixing of fuel air mixture, mixing of fuel with the air becomes the responsibility of not only the air swell, but also the fuel injection. That means, you would like to have as fine droplets as possible. And how can you generate fine droplets? By increasing the fuel injection pressure. So, therefore, the injectors that are used in a direct injection combustion chamber design have to have high fuel injection pressure. On the other hand, if you are talking about indirect injection, which are high swirl engines, okay, very fast swirl and turbulence. So, in that case, you can afford to not have high injection pressure. And there, if you inject the fuel at 200 bar, it is more than enough, because the turbulence is so high that even the large droplets will be able to vaporize. So, therefore, fuel injection pressure, what kind of, and obviously, as you keep on increasing the fuel injection pressure is a parameter which does not come free of cost. I will give you an example. If you go to market and buy a genset fuel pump and fuel injector, the whole set is going to cost you 2,000–3,000 rupees. But if you go and buy a fuel pump and fuel injector set for a common rail direct injection engines, it is going to cost you a couple of lakhs. Okay. So, this is not free of cost. This one is 200 bar, the other one is 1600 bar or 1800 bar. Okay. So, what I am trying to say is that the moment you start increasing the fuel injection pressure, the cost of fuel pump and fuel injector and the kind of sophistication required also goes up. Okay? And therefore, this is one parameter that when you are making a product, you have to be worried about the cost, because ultimately the customer does not want to know what you have paid for the fuel pump or fuel injector. He is only concerned about what he is paying for the whole package, that means whole engine how much he is paying, or for the whole vehicle how much he is paying. So this is very important. So one of the most important thing when we are talking about engine design or automotive design is we have to always keep in mind the end user, the customer. He has to see a value proposition by increasing the fuel injection pressure, how much benefit you are getting in terms of fuel economy, which will be of direct interest to the customer. You can design a fantastic engine, but if it costs 10 lakhs or 15 lakhs, whereas competitor is selling one for 1 lakh, who is going to buy your engine? It may be very good, nobody is going to buy. So when you go into industry, all these factors need to be kept in mind. Anyway, so the third factor that one has to keep in mind when you are designing good combustion chamber design is nozzle. So in the injector, there could be 1 nozzle, there could be 3 nozzles, there could be 4 nozzles, 6 nozzles, 8 nozzles, 12 nozzles, depending on how big is the engine, what are the areas that you are targeting. Again, it is also related to cost. What's the size of those nozzles? They're 100 micron, 120 micron, 150 micron, and so on. And what is the arrangement? That means what is the cone angle that they make, and what is the relative angle between the nozzles. So all those things have to be kept in mind, and also you have to keep in mind the maintenance, because ultimately at the end of the day, diesel engines require higher maintenance than gasoline engines. So your combustion chamber design should be such which should be easy to maintain. If just to take a cylinder head out, if you have to almost dismantle the whole thing around the engine, it's going to be very inconvenient for the mechanic who is going to maintain it. So it should be such that just by opening 4 valves and without much of a trouble, you will be able to maintain it. What's the kind of ease of starting? What is ease of starting? Ease of starting, I think in previous lectures we discussed that in the cold start conditions, sometimes it is very difficult to start. Why? Because you have very large surface area. As soon as on a cold winter morning you start cranking, the air gets heat up because of compression, but because of the large surface area, all that heat is taken out. So you find it difficult to start. So again, the heat loss to the combustion chamber wall in a way is related to ease of starting. If you have low heat loss to the cylinder walls, then ease of the starting will. So ease of starting is also in a way directly related to combustion chamber design. Then fuel requirement. What kind of a fuel would you like to operate? For example, if you're designing the engine for a car, okay, where do you have to operate the car? You have to operate the car in cities, and cities require that now in India most cities require that you should meet Euro 4 emission norms, okay, otherwise your car will not be allowed to run, right. So there you will be using more sophisticated fuel, more refined fuel, because you have to meet higher emission standard. But suppose you are designing a fuel, a combustion chamber or engine combustion chamber for ship which has to go to ocean. There the emission parameter is not as strict, because you will be ocean going liner, even if it pollutes a little bit more, it is all ocean and there is nobody around it, right. It's not, I'm not saying that there is no emission norm, but what I'm trying to say is that when you design for such kind of applications which are not directly affecting the public health, you can afford to use cheaper fuels. Locomotive, the locomotive fuels are also relatively inferior. For example, ship fuels, they are, when we did discuss the refining, we discussed that there is heavy diesel oil and all those kind of stuff, heavier stuff that comes out of the refining process which goes into it. In fact, sometimes even the ship fuel has to be maintained at 140 degrees centigrade in order to maintain its flow property. So it's that bad fuel. I mean, at room temperature it's almost solid, okay. So or slushy stuff. So depending on what kind of fuel you are going to use, again it affects the combustion chamber design. How much air you would like to utilize? Obviously you would like to utilize as much air as you can, because the amount of air is dictated by what is the swept volume, and air utilization. If you are able to utilize more air, that means you are able to put more amount of fuel into the combustion chamber, and therefore you are able to generate more power. If your air utilization efficiency is low, obviously for the same swept volume your power output is also going to be lower, right. So, I think this also is dictated in a way by combustion chamber design. Then power output to engine weight ratio, power to weight ratio is extremely important. Okay. For example, if you are designing a combustion chamber for a mobile application, you would like to have a lighter engine, right, because the engine has to carry itself. If the engine, instead of being 100 kilo, if it is 300 kilo producing same power, that means you will be, your passenger carrying capacity is now reduced by 200 kilos, right. But this is not applicable if you are deciding to design a generator engine. It does not matter whether it is 100 kilo or 300 kilo, right. So, combustion chamber design also affects power to weight ratio. So, that is also something that you need to worry about. Then combustion chamber design also affects whether you are designing the engine for constant speed operation or variable speed operation. For example, if you want to generate run the engine at 1500 rpm all the time, and the objective is to generate electricity. So, then designing of the combustion chamber is slightly different than the one that you will design for mobile application, because in mobile application it varies from say 700-800 bar all the way to 4,000-5,000 rpm, 700 rpm to 5,000 rpm, not bar. Okay. Then the combustion chamber design also affects the smoothness with which the forces which are generated by the expanding gases, they are transmitted to the piston. Okay. So, there if you have a bad design, then piston will be suddenly impacted by the gases, and as a result you will have jerky motion, not very smooth motion. So, you can see these are the important factors which you have to keep in mind when you are designing a combustion chamber. Okay. So, shape of the combustion chamber actually determines the quality of combustion and quantity of combustion, quality and quantity both. And since it is determining quality and quantity of combustion, it affects the performance characteristics, it affects the emission characteristics. Okay. So, combustion chamber therefore becomes extremely important. Diesel engine combustion is greatly influenced by air turbulence, and air turbulence is created by the shape of the combustion chamber area. So, when you say combustion chamber design for a diesel engine, what are we trying to say? What does it constitute? Does it constitute the cylinder wall? Yes. I mean, but cylinder wall design you can't change, it has to be circular. Does it constitute the cylinder head? Yes. So, the cylinder head design you can change. Does it constitute the piston? Yes. So, when you say engine design, engine design in terms of CI engine combustion chamber design, you are essentially talking of design of the cylinder head and design of the piston, that is about it. Okay. And each combustion chamber shape creates its own very unique turbulence pattern that is right for some application, while it may be wrong for some application. Some combustion chamber designs may be good for generator application, they may not be good for transport application. Some designs may be good for small applications such as say car, and they may not be good for locomotive or ship applications, and vice versa. So, there is no one single solution for CI engine combustion chamber design which fits all because of these reasons. Okay. So, if you classify two main classifications, direct injection, indirect injection, all of us know this. So, direct injection combustion chambers of compression ignition engine, they are also known as open combustion chamber. Okay. And IDI is not called closed combustion chamber, opposite of this, it is called divided combustion chamber. So, open combustion chamber and divided combustion chamber. So, what does the open combustion chamber means? Open combustion chamber means that the entire volume of the combustion chamber is in one piece in the main cylinder. Main cylinder volume, it lies there. There is no other volume which can be called combustion chamber. Okay. And fuel is directly injected into the main combustion chamber. There is only one combustion chamber, main combustion chamber, and fuel is directly injected into it. And the second type is IDI, or indirect injection combustion chamber. For most applications, IDI for all practical purposes is a dead case. It is not used for most applications because it is not able to meet emission regulations as on today. There are very few applications, and I will tell you, but it is of good academic interest to see why and how it was used, and obviously IDI, my expectation is that IDI combustion chamber will come back at some point in time. Okay. So, from that point of view, let us try to understand what are the strengths and what are the weaknesses of this particular design. DI combustion chamber is all over the place. I mean, if you pick up any vehicle, it will definitely be a DI combustion chamber. So, in IDI combustion chamber, it is divided into two main parts. One part is a part of the main cylinder, and the other one is a part of the cylinder head. So, combustion chamber, half of it is in the main cylinder and half of it is inside the cylinder head, okay, and they are connected by a nozzle, okay, a passage. So, IDI combustion chamber can be further differentiated into three parts. One is called swirl chamber, the other one is called pre-combustion chamber, and third one is called air cell chamber. These are the three further classifications of IDI. So, in swirl chamber, swirl is generated by compression. So, this is compression swirl dominated, and in pre-combustion chamber, this is combustion generated swirl. Okay. Pre-combustion chamber is also called turbulent chamber. So, generally during the compression stroke you generate turbulence, and then when the combustion takes place, swirl is generated. Air cell chamber is basically nothing but hybrid of both of these. Okay. So, both compression and combustion swirl are induced in this. Okay. But if you ask me, this is not so important. These two are the mainly important IDI combustion chamber designs for compression ignition engines. Okay. Now, let us first try and understand direct injection combustion chambers. So, direct injection combustion chamber has a single cavity, only one cavity, and these chambers mainly consist of space formed between flat cylinder head. Mostly, you know, in DI engine the cylinder head is mostly flat. So, now you have round liner, flat cylinder head. So, now when you say DI engine combustion chamber design, essentially you are talking about piston bowl geometry, that is about it, okay, and a cavity in the piston crown of different shapes. So, basically DI engine combustion chamber is different piston shape designs, right. Nozzle injector could be multiple holes. So, since it is flat head and this is direct injection, most of the time you have multi-hole injectors. Only one case you have a single hole, I will tell you what that is, and these are generally working at relatively higher pressures above 200 bar. 200 bar is the lowest, cheapest, filthiest engine, DI engine that you have, it is not clean. So, DI engine combustion chambers have made a lot of progress in terms of fuel injection pressure, and they have gone up to 1600, 1800 bar pressures are commercial today, and CRDI, common rail direct injection, is a variation of this. It is a direct injection, it is a type of direct injection. And now the research is going on to introduce fuel injection pressure as high as 2500 bar. So, fuel injection pressures are just going off the roof. Okay. So, fuel is directly injected into these shapes which are cavities, and not much of pressure difference between parts of the combustion chamber. So, in different parts of the combustion chamber, corner and the center or periphery, pressure is almost same because there is no division, it is just one single piece. So, it is almost same. So, in 4-stroke engines, induction swirl is generated by careful design of intake air passage or by masking the portion of circumference of the inlet valves. So, now if you have to generate swirl inside the combustion chamber, this is your direct injection combustion chamber. Here you have injector. Okay. So, what you do is this intake, if the air is coming in like this, you change the shape of the intake manifold such that when the air comes in, and then do the masking of the valves on one side, so that when the air comes, it is having a swirling motion. So, this is achieved by doing two things. One is careful design of the intake manifold, and then masking a portion of the circumference of the inlet valve. These are the two things that can be done. In two-stroke engines, induction swirl is generated by suitable form of inlet ports. Two-stroke engines, direct injection engines, are mainly used in ship engines, not in any transport applications. Okay, or they are used in, I mean, for even for small applications, I think they are not used. So, if you look at the direct injection engines, there are two design philosophies for the direct injection combustion chamber. One is the high swirl design, the other one is low swirl design or quiescent engine, low swirl design or quiescent engine. So, high swirl obviously means that the swirl ratio is quite high. I will define this swirl ratio. Swirl ratio is, see, when the air is coming in, it is having certain RPM, rotations per minute, and then crankshaft is moving at a certain RPM. So, this RPM divided by this RPM is defined as swirl ratio. Okay. Then you have low swirl. So, if you do not make these kind of things, then the engine will have low swirl, and quiescent, that means air movement is really very slow inside the engine. So, they are characterized by shallow bowel in piston and a large number of holes and higher fuel injection pressure. So, please understand the difference between these two very carefully. If you have a high swirl design, that means the air movement is very fast. So, what will happen to the fuel injection pressure? You can afford to have low fuel injection pressure, because the fuel air mixing can be achieved by swirl. So, just by designing the intake port masking the valve, intake valve, you can afford to have a fuel injection system which is not generating such a high pressure, cheaper system. It affects the cost. On the other hand, if you are going for low swirl, but then high swirl also affects the heat transfer. So, if you are going for low swirl engine, suppose your engine cylinder is very large, you must have seen that for large applications such as ship engines, so you must have seen large oil tankers, those large oil tankers which have pistons as big as 1 meter diameter, okay, and you have centrally located injector. So, there you do not want to have too much of swirl, so you keep it quiescent, but then you want the fuel air mixing, because fuel air mixing to be very good, because since the design of, the diameter and dimensions are very, very large, these engines will be typically very slow. How slow? They could be operating something like 60 RPM to 120 RPM. So, that means you have lot of time available to you, and since there is a lot of time available to you, you do not want to have turbulence, because turbulence and swirl, it increases the heat transfer. Okay. And for ship operation, economy of engine operation is very important, because that is where you make the money, right. That is where the ship operation is all about business, right, all business proposition. They can invest heavily in they do not mind investing heavily in the fuel injection system, and then you can have very high fuel injection pressures, because the fuel need to penetrate such long distance, you anyway need high injection pressures. Okay. So, low swirl engines, typically you require very high injection pressure, and these are generally very big engines. So, since there are big engines, and suppose you have 1 meter diameter and only 4 sprays going in 4 directions, that means there will be lot of air that will not be utilized in between the sprays. So, as a result, you can have better utilization of air by increasing the number of holes in the fuel injector. Okay. So, you have large number of holes, and you have shallow Bowline piston. So, generally you know, if you look at quiescent combustion chamber design, I will just make the top part of the piston. So, this is shallow piston design. Here you have centrally located injector, and these are the sprays. This is shallow design. Okay. This is more used in the automotive engine. This is called Bowline piston. Okay, and you have the injector which is injecting fuel like this. I mean, I have located it a little down, it will be here, and it could be like this. Okay. And there is another combustion chamber which is called M type, and here you have only one single jet. I told you this is a DI engine, and this is called M type. This is Bowline piston design, and this is quiescent design. Okay. So, these are the 3 different designs. So, these are the 2 philosophies of the design of the combustion chamber. So, obviously, when it comes to smaller engines, what would you like to have? Smaller engine, suppose you want to have a engine for car application. Which philosophy will you go? The top one or the lower one? What will be more suitable? A low swell or a high swell? So, obviously, you will go for high swell because you do not want to invest too much in the fuel injection system, and also you know smaller engine has to be very agile. That means it has to run at a fast speed. Okay. And since it has to run at fast speed, your fuel air mixture should mix quickly and burn quickly, and that can only be achieved by high swell, not just by fuel injection pressure. Okay. So, bigger engines are more quiescent type. Okay. Understood? So, the advantage of direct injection engine is that minimum heat loss during compression due to lower surface to volume ratio. You have the lowest surface that is exposed to hot gases in DI engines. When it comes to IDI engines, so I will show you. This is your DI engine combustion chamber, and this is your IDI engine combustion chamber. Here you have the fuel injector. So, in which case you will have higher surface area? Obviously, in this case, because there is a lot of surface area available. So, heat losses are much higher in case of IDI engines and much lower in case of DI engines. So, this is one of the positive aspects of DI engine. Since there is a surface area is very small, there is no cold starting problem. You can very easily start the engine during winter time, and you are using very high injection pressure most of the time. So, fine atomization can be achieved by multi-hole nozzles, and this also helps in avoiding the cold starting problem. But there are certain disadvantages. If you are going for direct injection system, then you know high fuel injection pressure is must. You can't manage with 50 bar. Okay. So, the fuel injection system is much more complex compared to SI engine or even compared to IDI engines, and more expensive also. And then you know accurate metering of the fuel is required. Exactly, you have to be very precise to milligram level. In every stroke, you have to make sure that you are putting not 1 milligram of fuel extra, because if you put 1 milligram fuel extra and you multiply this by whatever number of RPMs you have and per hour, you will be wasting 10% of the fuel. So, accurate metering of the fuel is extremely important. So, this is the shallow depth chamber. This is also called quiescent chamber. Depth of the cavity provided in the piston is quite small. Okay. So, this is quiescent engine. This is used in large engines which operate at slow speed, such as ship engines. Since cavity diameter is small, squish is negligible. I will tell you what is the squish in little later. Squish is a type of air motion. Okay. Then there is a hemispherical design. This is not very popular. Small squish is obtained, and the depth of the diameter ratio to the cylinder chamber can be varied for obtaining any desired squish or better performance. I will quickly show you some of the designs of the CI engine combustion chambers. This is also a cylindrical chamber, okay, basically truncated cone with a base angle of about 30 degree. Okay. Swirl is produced by masking the valve for nearly 180 degree of the circumference. So, if you look at the valve, 180 degrees masked. Squish can also be varied by varying the depth of the engine. Squish is nothing but the motion that you generate inside the cavity. Okay. Then there is a toroidal chamber. Here, you know, adequate squish or air movement can be obtained. Mask needed at the inlet valve is very, very small, and cone angle of spray for this kind of chamber, cone angle is this between the two sprays, is 150 to 160 degree. So, these are the typical direct injection engine combustion chamber, but these are the more prominent ones that are used. I will show you some of the pictures of these combustion chambers. Now, let us discuss briefly the IDI combustion chamber. So, IDI combustion chamber is divided into two or more distinct compartments which are separated by restricted passage. So, you know, please see this, this is the cylinder block, this is the piston, and this is the cylinder head. So, here you have some part of the combustion chamber as a part of the cylinder, and here you have another part which is a part of the head. So, combustion chamber is therefore divided in main chamber and pre-chamber or swirl chamber, whatever you may like to call it. Okay. And you see here nozzle or injector is located in the cylinder head, and it is giving fuel to the pre-chamber, not to the main chamber. So, assume that, you know, this piston is moving, first it is intake, and then when the compression takes place, what will happen? So, pressure will increase here, and through this passage the pressure, the air will move in, and when the air moves in, you know, this is a typical design. So, air will move in a certain direction and it will generate swirl or turbulence. It will generate swirl because the design is such that it will generate only swirl. So, air will be moving extremely fast inside this when the piston is moving up, and then you inject the fuel. Now, here the fuel is not injected at a very high pressure, it is injected at a relatively low pressure, 100, 150 bars. So, the droplet size is quite large, but then it is interacting with fast swirling air. So, it mixes, and when it mixes, what happens? Combustion will start, each of the droplet will vaporize and localized combustion will take place, and then what will happen? The pressure here will increase. Once the pressure increases higher than this, then what will happen? The flow of the burning mixture will take place. All the fuel is injected here, but the air contained in this chamber is only 50%. 50% air is in the main chamber. So, combustion will start here and combustion will end in the main chamber. Clear? And then, you know, I told you that in IDI engine it is difficult to start the engine. Why it is difficult to start? Because surface area is very large. Suppose in a cold start morning you want to start and you compress, air comes in, but then, you know, there is a large surface area, it is all enclosed by metal. So, all the heat that you will generate because of compression, isentropic compression, will be taken up by the metal, and you keep cranking, it will not start. So, in order to avoid that, what happens is you put a glow plug. Glow plug is nothing but a ceramic heater. So, before starting, you just press the glow plug becomes red hot. Once it becomes red hot, it will do radiative heat exchange with the walls and its temperature will rise. So, when you crank, engine will start, right. So, combustion chamber is divided into two or more distinct compartments separated by restricted passages. A considerable pressure difference is created between them during combustion process. So, when the combustion happens, pressure here in the pre-chamber will be more, in the main chamber it will be less. Okay. Spherically shaped chamber separated by the engine cylinder and is located in the cylinder head. About 50% of the air is transferred into this chamber during the compression stroke. So, the volume when the piston comes at TDC, half of the volume is here and half of the volume is here, 50%, right. And then the air enters in the swirl chamber tangentially from the main cylinder and there is a strong rotary motion inside the swirl chamber that is generated because of the shape. Okay. And then after combustion the products rush back into the cylinder through the throat, this is called throat. So, pressure here increased and then all these will go into throat with a very high velocity, much higher velocity than what the air, when the air went in, because here now the pressure is significantly higher, lot of heat has been released by because of the combustion of the fuel. So, what are the applications? So, one of the main application is, see here you are able to generate combustion with fuel droplets which are large. You are able to generate combustion with fuel which is poor in quality. Even the lower fractions of your fractional distillation column if you put, you will still be able to generate combustion here. Pressure system, that fuel injection pressure system that you are handling is also a low pressure system. Low pressure system will be very coolly able to handle poor fuel quality, right. If you have a CRDI system, you need extremely sophisticated and more refined specification controlled fuel, but here not so. So, one of the main advantage of this technology is that even if the this can really accept poor quality fuel. Okay. Obviously, if it accepts poor quality fuel, it will emit a lot of bad emissions also, but at some point in time that was not a major concern. It is a major concern now, but 20-30 years back it was not. And you know, you must have seen that the Tata Indica engine, it was also a semi IDI kind of engine. So, we have had IDI engines till quite recently, about 10 years or 15 years back. Okay, but now they are completely banned. Okay, no engine in India is sold with IDI for automotive applications. Here you see this is a single hole nozzle of large diameter of fuel spray which is used in mostly in IDI engines. So, single hole nozzle, cheap nozzles. So, this engine is actually a cheaper engine. Another design of IDI, this is called pre-combustion chamber or turbulent chamber. This is swirl chamber design, this is turbulent chamber design, and here also you can see this is the piston, this is the pre-chamber. But something very interesting you see here, when the piston goes up, will there be any direction? No, because it is symmetric around this axis. So, when the air enters, half of the air will go this way, half of the air will go this way, and there is no particular pattern and there will be no swirl, rather there will be lot of turbulence. Okay. So, that is why this is called pre-chamber or turbulent combustion chamber. So, pre-chamber is also located in the cylinder head, around 40% of the total combustion space is here. So, this is slightly smaller than the swirl chamber. Swirl chamber had about 50% space and this is about 40%. During compression, you know, piston forces the air into the pre-chamber just like the earlier case. Combustion is initiated by fuel injection into the pre-chamber, here the fuel injection is taking place. So, then you know, due to high pressurized combustion product rush into the main chamber at high velocities. So, this is just like the other thing, the only difference is the design. Okay. A strong turbulence is created which distributes the flames, which distribute the flaming fuel well into the well within the air into the main combustion chamber. So, flames will actually rush into the main combustion chamber. Bulk of the combustion takes place in the main combustion chamber and 80% of the heat is released in the main combustion chamber. You want to release most of the heat here. Why? Because if you release most heat here, there will be more heat loss, right. So, rate of pressure rise and maximum pressure is lower compared to those of open type combustion chamber in this case. Now, this is air cell design. I will not go into detail of it, but please understand this is the main chamber. Okay. Then there is one small chamber here and there is one main chamber here. These are called, this is called, both of these are called two-part energy cell. This is small energy cell and large energy cell. And here in pre-chamber and swill chamber, the injector was located in the pre-chamber, but here the injector is on the other side. So, when the injection takes place, some fuel is in the main chamber, but some fuel enters the energy cell and then slowly comes back into the main cell. So, this is how the flow is. This is the sectional view and this is the view from the top side. When the fuel injection takes place, it is sending directly the fuel into the main combustion chamber, and when the flames come out, they will go in this direction, they will also go in this direction and form a swirl inside the chamber, main chamber. Okay. So, I will not go into the details of it. Now, what are the advantages? We have seen the advantage and disadvantage of direct injection combustion chamber. Let us look at the advantage and disadvantage of indirect injection combustion chamber. So, first advantage is that the fuel injection pressure that is required by IDI engines is really low, okay, compared to DI engines. It has excellent mixing and turbulence characteristics, very fast air swirl because of the design of the combustion chamber itself, okay. And then direction of spray is not very important, even if you do 5 or 10 degree here and there, it does not matter, it is not going to affect the emissions, it is not going to affect the performance, but you cannot do that in case of DI engines, it is extremely important. And it can burn low quality fuels, extremely important quality. It has low noise and exhaust emissions, except particulates are more, but generally the exhaust emissions are lower. When say exhaust emissions, you are talking about HC and CO, they are generally very low. PM and NOx can be higher in this case, so especially NOx can be higher, okay. What are the drawbacks? There are certain issues with the IDI engines. So, one of the drawbacks is a very high temperature and pressure in the pre-chamber. Wherever you are injecting the fuel, you have very small air, 50% of the 40% of the air, and all the fuel is being dumped, entire quantity. So, this particular area, this particular small chamber will experience very high temperature, and because of this very high temperature, NOx formation will be more. We know because NOx formation is a function of temperature, peak temperature. Higher is the peak temperature inside the combustion chamber, higher will be the NOx formation, and NOx formation is given by Zeldovich mechanism, right, you all know this. So, and then the other drawback is that there is a requirement of heater or a glow plug. If you do not have a heater or a glow plug to heat the pre-chamber, you will have serious issues with cold starting. So, I mean once you put glow plug or heater, you also need a battery system which is powerful enough. Even in the most cold weather, severe cold condition, it should be able to give you enough current, and there should be enough current still left to crank the engine, otherwise you will not be able to start. The other thing is that the specific fuel consumption is very high. Why it is very high? Because of the pressure loss during the air motion when it is coming from the main chamber via the throat. So, there is some pressure loss there, and then there is large amount of heat loss because of high temperature gases being exposed to large surface area, okay. And because of this region, SFC is very high and they are also less efficient, okay. So, DI engines are more efficient, IDI engines are less efficient, and they also have bad NOx emissions, even particulates sometimes can be very high here, okay. So, this is as far as the very high level we have seen, we have compared DI and engine combustion chamber designs with IDI combustion chamber designs. Now, let us look at these combustion chambers in a little bit more detail at say flame level or at let us say spray, what happens in that chamber, okay. So, let us first look at the spray in diesel engines. So, first let us define the swirl ratio. So, swirl ratio is defined as the ratio of air rotational speed around the axis of the cylinder to the crankshaft rotational speed, that is the swirl ratio, okay. Adequate mixing of the air fuel is enhanced by a swirling action. And engines are generally designed with a specific swirl ratio of typically about 2.5. If you have 2.5 in your DI engine, you are okay. That is the target, okay. And this 2.5 number has come from experience. People have designed all kinds of shapes and sizes and seen, you know, different swirl ratios and then come up that, okay, this 2.5 gives you the best performance, okay. So this is one of those thumb rules in automotive industry, or what we call as empirical relationships, okay. So here you see you have a helical design of intake port and then a masked intake valve. So if the air is coming and the intake manifold design is such that the air, you are giving a slightly rotational movement to the air, and when it passes through it, it rotates in the cylinder. So air intake being directed and swirled as it enters the combustion chamber. Now you see here, this is the cylinder and there is swirl. Obviously DI engine will definitely have swirl, whether low or high, that is a different thing, but it will have swirl. And in the center you have injector. Suppose this injector is taking out 4 sprays and there is swirl. So you see here, if the spray does not hit the cylinder walls, then you know the air is moving, this is the air and this is the spray. So spray will be affected by the movement of the air. So you can see the spray actually start a little bit turning and mixing, okay. And corresponding and then the spray, you know, outer periphery will start burning wherever you have the flammability limit being achieved. So when the flames come, these will be the probable ignition sites on the surface of the spray, and this is how the combustion will happen, okay. There may be a possibility that the spray actually hits the cylinder wall and it wets the cylinder wall. Say for example in this case, if your spray is penetrating deeper into the combustion chamber, it is possible that it may be hitting the cylinder wall. So if it hits the cylinder wall, then the combustion will be like this, it will be reaching the cylinder. This is not a very desirable situation though. Why? Because if the liquid fuel is reaching the cylinder walls, the fuel will mix with the lubricating oil, and as a result it will dilute the lubricating oil. It may even go back to the sump. So when the lubricating oil goes back, there may be some fuel also going back, and fuel is lower viscosity, so it will reduce the viscosity of the lubricating oil in the sump, and as a result the lubrication efficiency of the engine will be compromised. So it is not a very desirable situation, but this is just an example that what happens in the combustion chamber when the spray is hitting the cylinder wall and not hitting the cylinder wall, okay.